Let's write a theorem of 5 sections, and the theorem is going to satisfy this title. It's going to be some properties of the kernel in the image. So here it is. So suppose that T from V1 to V2 is a, or let T be a, where is it? Let T be a linear transformation, linear map. Then, 1, the kernel of T is, we know that it's part of V1, it's a subset of V1, right? It's elements in V1 that satisfy something, namely that T sends them to 0 in V2. But the claim is that it's not just any subset, it's a subspace, a subvector space of V1. We said it, we mentioned it, but we never proved it. Let's do it. 2, the image is a subspace of the range of V2. Not just a subset, a subspace. 3, T is 1-to-1. 1-to-1 is a function. You know what a 1-to-1 function is. A function is called 1-to-1. And remember that a linear map is, to start with, it's just a function, right? It's a function that satisfies 2 more properties, the linearity properties. But as a function, it can be a 1-to-1 function. And a 1-to-1 function means that if you take 2 different guys here in V1, T sends them to 2 different guys here. It doesn't send 2 different elements in the domain to the same element in the range. Okay, that's a 1-to-1 function. T is 1-to-1 if and only if the kernel of T is 0, contains only the 0 vector. Okay. 4, T is onto its range, onto V2. So what is an onto function? An onto function means that every element in the range is indeed the image of some element in the domain. Okay? So T is onto if and only if the image of T is all of V2. In fact, number 4 is here just for the statement to be kind of complete. Number 4 is a definition. It's not a theorem. That's the definition of being onto. Do you agree? A function is onto if its image is the entire range. Do you agree? Okay, so this is not really a theorem. This is, in fact, a definition. Nevertheless, I want it written here because you can see the duality, the nice duality, and it's easy to refer to. And number 5 is a bit different in it. Maybe we'll throw in number 5 as a separate theorem later. Let's handle these 4. Okay? So let's start with 1. I want to show that the kernel is a subspace. How do we show that something is a subspace? It has to satisfy all the property of being a vector space with respect to the same operations in the ambient space in V1. Okay? But we know a theorem that we don't really need to check all of them. It suffices to check that it's not empty, closed under linear, under sums, and closed under scalar multiplication. That's it. Okay, so let's do it. Proof of 1. So we want to show that the kernel is not empty. Right. We know T of 0 is 0. This we proved before. Remember? 0 is always in the kernel. Therefore, 0 belongs to the kernel, right? Because T sends it to 0. And therefore, the kernel is not the empty set. Do you agree? Good? So this is one thing we need to show. The other thing we need to show, we need to take two guys in the kernel, call them U and V, in the kernel, and show that U plus V is also in the kernel. Okay? So if U and V belong to the kernel, this is our W now, this is what we're claiming is a subspace, then what does it mean that they belong to the kernel? It means that T of U is 0 and T of V is 0. That's what it means to belong to the kernel. Therefore, what is T of their sum? U plus V. T is a linear transformation. T of a sum is the sum of the T's. Right? That's the property of being a linear transformation. And since both of them are 0, it's 0 plus 0, which is 0. Therefore, if U and V are in the kernel, T of U plus V is also 0, and therefore, U plus V is also in the kernel. Do you agree? Likewise, if V is in the kernel, then, by definition, T of V is 0. Therefore, T of alpha V, right, by being a linear transformation means that you can pull out the alpha. That's the second property of being a linear transformation, right? And this is alpha times 0, which is 0. Therefore, alpha V is in the kernel as well. Good? So these three bullets show precisely the necessary conditions and the sufficient conditions for being a subspace. Do you agree? Good? Okay. Proof of 2. Proof of 2. Homework. Same idea, very, very similar. Try to do it on your own. Okay, good? Let's prove number 3. Proof of 3. So let's recall what 3 said. Let's go back to the theorem itself. Remember that we don't need to prove 4, because 4 is just the definition. A function is onto if and only if the image is the entire range. But we do need to prove 3. So 3 is a statement, an if and only if statement. Therefore, we need to prove both directions. And we're going to prove them separately. So the first direction is, if t is a one-to-one function, then the kernel is trivial. Only zeros in the kernel. Second direction, if the kernel is trivial, then t is one-to-one. Question?
Why isn't it a definition? Because we're defining if t is called one-to-one.
No. 3 is not a definition. 3 requires proof.
That's what I'm asking. Why is it? I mean, is one-to-one isn't it a name for t in that situation?
No, a function is called one-to-one. If you take two different guys, they get sent to two. If x is different than y, then f of x is different than f of y. That's the definition of being one-to-one. It doesn't have a priori anything to do with the kernel. Right? In calculus, you saw the definition of a one-to-one function. You never mentioned the kernel. Right? These are two different notions. Okay? They're not different. It turns out that they're, well, they are different. The kernel is 0 is the same as being one-to-one, but that requires proof. Okay, good. Here, it's precisely the definition. That's how we defined an onto function. Okay? Okay, and if you haven't seen these definitions, so the definition of what being one-to-one is, I'm going to write in a minute. So you're going to see it. The definition of being onto, I'm going to tell you what it is. It's precisely this. The definition of being onto is the fact that the image is everything. Okay? Okay, so let's prove 3. So, first of all, this direction. This direction. Assume that T is onto. That T is 1-to-1. What it means, by definition, that if you take U and V that T sends to the same image, if T of U equals T of V, that can only happen, that implies that U was in fact V. That's what it means to be 1-to-1. Okay? A different way of saying this, so assume T is 1-to-1. By definition, this is what it means. And this is equivalent to saying, a different way of saying the same thing, is that if U is different than V, then T of U is different than T of V. This and this are the same thing. This implies this is the same as not this implies not this. That's what I wrote here. The reason I chose this one is that this is what I'm going to work with. Okay? So that's the definition of being 1-to-1. The word kernel is not there. Do you agree? Okay? And it's not going to be there if it's not a linear transformation. Okay? It's only related, we're going to use the linearity. Okay? So this is what it means to be 1-to-1 by definition. Let's prove that the kernel is trivial. So how are we going to show that the kernel is trivial? What does it mean that the kernel is trivial? It means that the only guy in the kernel is 0. There's nobody else there. Okay? So a way of proving this, take somebody in the kernel. Call it V. I'm going to show that V is 0. And then I'm done. I took some general vector in the kernel and showed that it's just a 0 vector. Okay? So take V in the kernel. T of V is 0. Why?
Because it's in the kernel.
Because it's in the kernel. But we also know that T of 0 is 0. That's a general fact about linear transformations that we proved in the very beginning. Remember? So T of V and T of 0 are equal. Do you agree? And that implies T of V equals T of 0. We're assuming 1-to-1-ness. That implies that V is 0. So here we used 1-to-1. Where did we use the linearity here?
The one left.
Right, here. This we proved previously, and this is true for a linear transformation. Not every function takes 0 to 0, right? Not every function sends 0 to 0. A linear one does. Okay, a linear transformation does. Okay, so good? Do you see why this proves the claim? It's very simple, very straightforward, as long as you're clear on the roles being played by each guy here. Okay, what are we trying to prove? What do we know? Why did we show it? Everybody good?
Technically, if we wanted to prove this, shouldn't we have taken another U, say it belongs to the kernel of T, and prove that it's always, that U always equals V? I mean, technically.
No, I don't understand what you mean by technically. I claim that this is a complete proof. My claim is that the kernel is 0. There's nobody else in the kernel, only 0. I'm proving it. I'm taking somebody general in the kernel and showing that that somebody is none other than 0. Now you're going to say, take somebody else in the kernel. Why? Why do I need to take somebody else?
You took someone specific.
No, I didn't. I took V in kernel T, any V you want, not specific. Take any V in the kernel, boom, it has to be 0. That's it, only zeros in the kernel. Good? Everybody? Okay, but that's just one direction. Now we need to show the other direction. So now we're assuming that the kernel is 0. We need to show that it's a one-to-one map. Okay, so assume that the kernel is 0. Okay. How do we prove that it's a one-to-one map? I want to show this. This is what it means to be one-to-one. Okay. So take U and V such that T of U equals T of V. And we need to show that U equals to V. Right? If we show that if T of U equals T of V, that implies that U equals V, we're done. It's a one-to-one map. Okay? So take T of U equals T of V, and let's consider T of U minus V. So what is U minus V? What is subtraction? This is T of U plus the inverse of V, the additive inverse. That's how we define U minus V, right? That's the same thing. Good? Now we're using linearity again. What is T of a sum? The sum of the T's. So this is T of U plus T of minus V. What is T of minus V? In the same little lemma, the same little, right, the same place where we showed that T of 0 is 0, we showed that T of minus V is minus T of V. Okay? Obvious, because this is like a minus 1 here, you can pull it out by linearity. So this is T of U minus T of V. But we're assuming that T of U and T of V are equal. We took a U and a V that satisfied this, so this is just 0. Right? So T of U minus V is 0. Do you agree? What does that tell us about U minus V? It's in the kernel. We just showed that T of it is 0. The T sends it to 0. That means that U minus V is in the kernel. Do you see that? Okay, so I'm going to write it on the next board in a second. But we're assuming that the kernel is 0. So it means that U minus V is 0. Okay, so this implies that U minus V belongs to the kernel because T of it is 0. And in turn, this implies that U minus V is 0 because we're assuming in this direction that the kernel only contains 0. And therefore, U equals V. Good? Okay, so nothing difficult going on here. Everything is very straightforward. You just have to understand what you're assuming, what you're trying to prove, and how to express it. Okay, sometimes those are not trivial things. Even if, right, we didn't use any deep theorems here or the Steinitz exchange lemma or I don't know what. Very, very straightforward. You just have to understand the players. Who versus who. Okay? Okay. So this concludes the proof of that 4-part theorem. Now we know that the kernel and the image are in fact subspaces, and we know that the kernel is trivial if and only if the map is one-to-one. Okay? What I want to do is add another theorem. Maybe we'll write it down here. I even don't need to erase this. So another theorem. Let T from V1 to V2 be a linear map. then, oh, not then, I need another statement. If u1, u2, dot, 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 up to un span v1, so I'm taking a spanning set for v1, a bunch of vectors in v1, such that the entire space is all linear combinations of these guys. That's a spanning set, right? Then the set T of u1, T of u2, dot, 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 T of un spans v2. Okay? So if you take a spanning set, send the guys in the spanning set to v2, you get a spanning set for the range. Okay? For the image. Oh, mistake. Not v2. Fix this. They don't span v2. There's no chance for them to span v2 unless it's onto, right? They can only span what's obtained by t. They span the image of t, which is a subspace of v2. Good? Okay, let's prove this. So how do I prove it? How do I prove something like this? What's the logic behind it? So, not much. I'm going to take an element in the image, and show that this general element in the image is a linear combination of these guys. That's it, right? That's all I need to show. Do you agree? So take somebody in the image. What does somebody in the image look like? It's T of something, right? So take T of V. This is a general element in the image. I could say take some W in the image, but that's not capturing the fact that it's in the image. If it's in the image, it's T of something. That's what it means to be the image, right? So take T of V in the image. I want to show that T of V is a linear combination of these guys, right? What do I know? I know that V is a linear combination of these guys, because this is a spanning set, right? So V equals sum alpha 1 u1 plus alpha 2 u2 plus alpha n vn. Because V is somebody in V1. UN. Thank you. Beats me why I converted to U's here. They should have been all V's. But anyway. So V is a linear combination of these guys because this is a spanning set for V1. Therefore, what is T of V? T of V is T of this thing, T of alpha 1 u1 plus alpha 2 u2 plus alpha n un, right? By linearity, T of a sum is the sum of the T's. So this equals T of alpha 1 u1 plus T of alpha 2 u2 plus dot 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 T of alpha n un. This is the additive part of being linear, right? Now again by linearity, T of a scalar times a vector, the scalars can hop out. So this equals alpha 1 T of u1 plus alpha 2 T of u2 plus dot 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 alpha n T of un. Do you agree? And that's it, I'm done. I showed that I took somebody in the image, it's a linear combination of these guys. Done. Okay? The step from here to here, which I did in 2 steps, is very, very standard. We're going to do it in many, many, many examples and proofs and all the time. When you have T of a linear combination, it's the linear combination of the T's of the original ones for any linear transformation. Okay, so this step is, you should really feel why it's a very, this is the essence of being a linear transformation, in fact. Good?
The V took is the one from V1, right? The
V is in V1.
So the T's of the U1, I'm talking about the last line. These guys are linear combination of the VU2.
No.
That's what the part I didn't understand in the end.
V is an element of V1. Therefore, it's a linear combination of a spanning set of V1. Therefore, T of V, now everything lives in V2. Once you T something, it's in the range. It's in V2. Okay? T of V is in V2. It's T of this linear combination. Being a linear map, I can take this step, which I took in steps, because it's the first time I'm doing it. And now I showed that T of V is a linear combination of the T's of the UIs. Good? Okay. So let's do an example. We've been rather abstract and theoretic in this clip. Let's do an example. Let's find the example. There it is. So, example. Let's take T going from M2 of R. What is M2 of R? Right, 2 by 2 matrices to R2 of X. These are polynomials of degree less than or equal to 2 with variable x and coefficients in R. Okay, I have to tell you what T does. This is just saying what the domain and the range are. Now I have to tell you what the rule is, right? That's how you prescribe a function. Okay, so T of a 2 by 2 matrix, call it A, B, C, D, is going to be a polynomial of degree less than or equal to 2. And the polynomial is going to be A plus B, that's the free coefficient, plus C plus 2D x, plus 2C plus 4D x squared. Good? We need to check that it's a linear map. Okay? And you need to check that it's a linear map. A clue, a way to see it, but we didn't prove this yet, is that every component of the image is a linear combination of the components of the element in the domain. Okay? Do you see that? So, because we said it, we already know that it's a linear map, but we didn't prove that yet, and you need to verify manually. Show that if you take two guys, T of one plus T of the other is T of the sum. Okay? Show that if you multiply by alpha, you get alpha times T. Okay? So verify that T is linear. Do it. Do it. Very important to do it. Okay. Let's see what the kernel of T is. So what is the kernel of T? The kernel of T is all the guys that get sent to 0. 0 is the 0 polynomial. So the kernel of T, it's a subspace of the domain. It's all the guys of the form A, B, C, D that satisfy that T of them is 0. When would this polynomial be the 0 polynomial? If A plus B has to be 0, C plus 2D has to be 0, and 2C plus 4D has to be 0, but that's already incorporated in the second requirement. Do you agree? So this is the kernel. Does everybody agree? Good? Okay. We can rewrite this. It's very specific, right? From here it follows that B is minus A. So it's going to be matrices of the form A. B has to be minus A. And then D is minus C over 2. So if here we have C, and there's no relation between A and C, there's no requirement of that sort, right? But D has to be minus C over 2. Do you agree? So this is the kernel. All the matrices of this specific form are precisely the ones in the kernel. Okay? And we can even write this. We can even easily find the basis for that. Right? It's all the elements of the form A times this matrix plus C times this matrix. Do you agree? So this is in fact the basis for this kernel, and I just wrote it as a span, but it obviously spanned by this. In order to say that it's a basis, we need to say something else. Right, that these two are linearly independent, and they obviously are, because one is not a multiple of the other. Okay, so let's write that. These are linearly independent, right? And therefore, this is a basis, this set of two elements is a basis for the kernel, not for V1. V1, the basis for V1, we can take the standard basis, right? 1, 0, 0, 0, 0, 1, 0, 0, etc. But this is a basis for the kernel, only for the guys that get sent to 0. And what's the dimension of it? So the dimension of the kernel is 2. Right? Because there are two basis elements. So these are linearly independent and thus a basis. Good? Okay, so this is the kernel. We deciphered what the kernel is, and we know its dimension. Okay? Let's try to understand what the image is. Do we get all polynomials of degree 3? If not, which ones do we get? What the image is? What are the polynomials in R2 of x that are T of some 2 by 2 matrix by this formula, by this rule? Okay, so in order to do that, what I want to use is the last theorem that we had that said, take a spanning set of the domain. We called it U1 to UN. Do T to it. That gives you a spanning set of the range. Right? That was the previous theorem. So, in order, so let's find the image of this T. In this example, we're in this example. So, here's a basis for the domain, M2 of R. I'm just going to take the standard basis that I know well. 1, 0, 0, 0, 0, 1, 0, 0. We called it E1, E2, remember? No, we called it E11, E12, E21, E22. Remember that notation? 0, 0, 1, 0, and 0, 0, 0, 1. There you have a basis for M2 of R. Okay? If we T these guys, if we do T of this, T of this, T of this, and T of this, we're going to get a spanning set for the image. That was the previous theorem. Let's glance at it for a minute. If you take a spanning set for V1, and a basis is, of course, a spanning set, do T to them, you get something that spans the image. And that's how we're going to decipher what the image is. Okay? So, T of these guys, let's find out what T of these guys is. So, T of these, this is not formal language. T of these, right? T is not a verb. Okay, but I'm considering T as a verb here. Okay, let's T these guys. T of them. Okay, I'm using T as everything, in fact. So T of these will give a spanning set for the image. That was the previous theorem. Do you agree? So let's find what T of these are. The formula is on the previous board. Okay, so let's glance at it for a minute. I want to do T of 1, 0, 0, 0. So I get a 1 here and zeros everywhere else. So T of the first element is just the polynomial 1. T of 0, 1, 0, 0, I get a 1 here and 0 everywhere else. So again, I get just the polynomial 1, right? T of 0, 0, 1, 0, 0, 0, 1, and 2, right, is going to be x plus 2x squared. Do you see that? And T of 0, 0, 0, 1 is going to be 2x plus 4x squared. Good? So let's write that. So we get the spanning set that we get for the image is 1, 1, x plus 2x squared, and 2x plus 4x squared. This is a spanning set for the image. Do you agree? Okay, by the previous theorem. Okay. Now, is it a basis? No, obviously they're linearly dependent. One of them just appears here twice, and this one is just double this one, right? So we can obviously throw these two away. They contribute nothing. They're linear combinations of the others. And then we're left with 1 and x plus 2x squared, which are linearly independent, obviously. One is not a multiple of the other. Okay, so good. Everybody followed these arguments? I'm not going to write all the details. I'm just going to write 1 and x plus 2x squared is a basis for the image. Any polynomial in the image is going to be a linear combination of these two guys. And obviously, this is not all the polynomials, right? There's no restriction on the free coefficient, but there is a big restriction on the relation between x and x squared. Do you see that? Okay. What is the dimension of the image? 2. The dimension of the image is 2. The dimension of the kernel was 2. They sum up to 4, right? Which is the dimension of the domain space. Okay? The dimension of the range space, by the way, is 3 in this case, right? Polynomials of degree less than or equal to 2 are is a 3-dimensional vector space, right? But the dimension of the image is 2. The dimension of the kernel was 2. They sum up to the dimension of the domain space, 4. Good, everybody? Okay, so we'll stop this one here. Everything we did in this lesson was kind of accumulate very basic facts, very basic ingredients that will enable us to do two major things we want to do at least in the near future. One is show that every linear transformation can be presented by a matrix, and the other is to show that rank nullity theorem in the context of linear transformations, namely that the dimension of the image plus the dimension of the kernel equals the dimension of V1. That's a theorem we're heading for. Okay, so to be continued.